Okay, hello everyone, and thanks for coming. Welcome to the tutorial on out-of-distribution generalization, shortcuts, spuriousness, and stability. I'm Yoav, and in the next 2 hours with Aahlad Puli and Maggie Makar, and all of you, we will talk about some fascinating works and travel through the thick and thin of machine learning's generalization abilities. So you can submit questions to us with the barcode on the right, and we will take them near the end of the tutorial. And you may find slides in PDF format using the barcode on the left. At the end of the tutorial, there will be a panel with the wonderful Danica Sutherland, Ilan Rosenfeld, and Aditi Raghunathan. So let's dive right into the topic of today's tutorial. So AI systems are able to perform tasks that seem to go well beyond the scope of their training data, like generating quirky images or rewriting text in style that does not naturally fit its content. However, there are also peculiar behaviors that occur in rather simple settings. For instance, here I asked ChatGPT and Gemini to generate an image of a one-humped camel in the snow. So the generated image has 2 humps, and it is really unclear why it happens. But if we take into account the fact that in nature, one-humped camels live in deserts where it is rare to have snow, while many 2-humped camels reside in the Gobi Desert, where it snows quite often, this might suggest some properties of the training data that lead to this type of behavior. Another example, which we borrowed from Tal Linzen, is where we ask which city is further north, London or Montreal. And again, it is difficult to summarize what drives the model's outputs, but the fact that Montreal is associated with colder climates, and so does northern locations, may suggest some potential reasons. And what we see here is pretty much that the bot says that Montreal is further north, although it does know that the latitude is lower. But generally, as Tal puts it, it seems very challenging to come up with a mental model of the tasks that models find challenging. So in this tutorial, we might not develop this type of mental model, but we are going to scope and talk about some problems that remain challenging for machine learning, even with all the advances of the last years. We will be focusing on supervised learning tasks, where with features X and a label Y. And the general setting is out-of-distribution generalization. So while most literature in machine learning relies on the assumption that the training distribution of X and Y equals the test distribution, so OOD generalization, which we are interested in, will study the cases where this equality breaks. And the model is evaluated on data that is qualitatively different from its training data. That is, p-train does not equal p-test. And this is a case commonly referred to as distribution shift. And of course, in many applications, this is the rule rather than the exception. So going beyond the kind of toy problems we talked about earlier, and to illustrate this challenge with a problem that we might care about more than generating camels, let's look at chest X-ray classification. So MedGemini here, a multimodal large model, achieves quite outstanding performance on a test set of Mimic CXR, which is in the bottom here, a data set that is included in its pre-training data. But for other data sets like CheckSprit, so these multimodal LLMs perform much lower than the original data set, and there is a significant gap from the best unimodal model trained on these data sets. So this pretty much just shows us that there is much to be desired from the generalization abilities of large models on these type of tasks. So to start scoping these problems, we should develop an appropriate formalism and language to talk about them. And this is slightly challenging because there are many, many ways that data could be out of distribution. And just to illustrate that with a little example, so we can see that within the distribution shift zoo, there are many species of out-of-distribution generalization. There are things going from the ancient past of robust statistics about outliers and heavy tail distributions into considering epsilon balls of KL divergence or some other divergence of interest around your training distribution, and to adversarial examples, which depend on your model. And then there are all of these other things that are on the slide. And our tutorial will talk about types of shifts that are somewhere in the union of all of these, or scope out a part of this union. And to make this more concrete, Maggie will talk in the next section, and I will kind of give sort of, I guess, a general definition here. So the defining features of the shifts we will talk about today are that, first, they are large shifts. So they are not like the epsilon balls I've just mentioned in the last slide, where on the left we have our training distribution and a small ball around that. And they are rather the shapes of the sets of distributions that we'll consider are kind of strange, and they can be large, and the shifts may be large. And the second defining feature is that these shifts will be structured. They will be shifts in factors of the data generating process. So what that means, concretely, is that some relationships between the features and the label will stay put, will stay fixed. So for instance here, we can change the background of images that we observe, but the correlation between the shape of the camel and the label, which here is camel, will stay fixed across all of the type of shifts we all consider. And this is in contrast to things like blurring an image, where blurring an image actually changes the relationship of all the features with the label. So this is not the case for today. Okay, so the tutorial will proceed as follows. We'll have 4 parts. In the first part, Maggie will introduce the problem definition with some defining examples. And then in the second part, Aahlad will talk about algorithms to solve this type of problems that Maggie introduced in the first one. Then we will talk about some gaps in existing literature to deploy the types of algorithms that we considered so far in real-world applications. And finally, we will kind of conclude with, well, what has been the main, I guess, happening in the last couple of years of how large models that entered this field changed it or reshaped it, and we'll conclude that. So Maggie, please. This is yours.
Okay. Thanks, Aahlad. And Yoav. Okay, so like Yoav mentioned, I'm going to kind of give some principled approaches in order to formalize a set of permissible distributions or the set of permissible shifts and formalize the learning goal. Starting with formalizing the set of permissible shifts, we're going to refer to the set of shifts as a coupling, and we will use a calligraphic P to denote that. This set includes kind of all the permissible distributions that we might see at training or test time. So our test distributions have to be drawn from this coupling. And I'll use E to index the different distributions that exist within the coupling. The important part here is that this coupling makes some assumptions about what are the parts that are shifting versus what are the parts that are stable. So, for example, couplings, and you have alluded to that earlier, the couplings that we will talk about in this tutorial can be arbitrarily far apart from each other, because instead of reasoning about distances between distributions, we will be reasoning about structured shifts, and specifically shifts in how different structures, different components in our distributions might vary. The way to kind of communicate and formalize how these structures exist, we will use graphs generally, or slightly more specifically, directed acyclic graphs to kind of communicate what these structures are. And I'll go through a list of about 3 couplings, but this list is non-exhaustive. And if you're sitting there thinking, okay, like, how do I map these couplings onto my problems? There is no good coupling or bad coupling. There's, like, things will vary based on an application-to-application basis. The first set of couplings is subpopulation shifts. So this type of coupling, each permissible distribution can be expressed as a mixture over different distributions of subpopulations. And different distributions within the coupling will have different proportions over each one of those subpopulations. So this lambda vector, which denotes the proportion of each subpopulation, can vary from distribution to distribution. but the factors that correspond to the joint distribution within a subpopulation is stable. So the DAG here might look something like this. And as a quick aside, let's just define what this DAG is. So in DAGs, or the notation that we will use grayed out nodes to denote a variable that is observed at training time. And we will use the square dashed node to denote a categorical variable. And some values of this categorical variables may be observed at training time, but some might not be observed at all at training time. One example of this kind of coupling is when we're trying to predict pneumonia. So I'll go through that example really quickly. Here, again, our goal is to predict pneumonia, and what we might have in our data, we're trying to predict pneumonia from images. So what we might have is 4 different types of subpopulations. First is men who are healthy, second, men who have pneumonia, women who are healthy, and women who have pneumonia. So in this case, the X, our inputs, are the X-rays, Y is the pneumonia status, and both X and Y are affected by the environment through this vector lambda, which defines the subpopulations. For example, if I'm sampling from a hospital E, maybe I'm equally likely to observe any one of those patients. But if I'm sampling from hospital E tilde, maybe men who are healthy are underrepresented and women with pneumonia are also underrepresented. So if I were to take the data from hospital E tilde, train a model, and then try to apply it to hospital E, that model might not do well because it might be encoding information about the sex of the patient when kind of predicting the outcome. The second set of couplings explicitly decomposes the permissible probability distributions into factors, some of which are assumed to be fixed. These are the black components, whereas others are allowed to be shifty or allowed to be unstable. The unstable portions are typically induced by a variable that we will use z to denote, and we will call this variable a nuisance variable. And again, common factors that are common across all distributions are stable. So here the DAG might look something like this, where we have, again, our X and Ys, but X and Y are both correlated with Z, and that's problematic because Z is affected by the environment that we're sampling from. We'll use this type of coupling a lot in the talk, so I'll give 2 examples that kind of illustrate what it's about. The first is predicting clinical outcomes, specifically diabetes or arthritis, using clinical notes. So in this setting, maybe we observe data from 2 different doctors, Dr. Alice and Dr. Bob. Dr. Alice tends to see patients who are more likely to have diabetes, whereas Dr. Bob tends to see patients who are more likely to have arthritis. But that's not the only difference between the 2. Another big difference is that they have different styles of writing. So whenever Dr. Alice sees a patient, she might say something like, "I saw an 89-year-old man," whereas Dr. Bob would say something like, "I saw a 70-year-old gentleman." So there's a difference in style here. In this problem, our inputs are the text and the clinical notes, whereas Y is the clinical outcome, here diabetes or arthritis. The nuisance here is the style of writing. And which clinician the data sampled from will affect the style. Now, a naive model that just takes X, the inputs, which are the text from the clinical notes, and tries to predict the outcome, might incorrectly learn to encode that if it sees a man, or if their input is a man, then that it must be diabetes, or the prediction might be diabetes. If it sees a gentleman, then the prediction must be arthritis. This is actually not a hypothetical example. This is a paper by Feder and collaborators in 2023, showed that if you train the data using one healthcare data set, the MIMIC data set, and you try to apply it to a slightly different data set, the I2B2 data set, you see a drop in accuracy that is about or greater than 20%. Another example here is if I'm trying to predict what type of animal exists in a picture using images as an input, and if my data set is collected from like naturally occurring distributions or naturally occurring settings, the majority of camels will appear against sand, and the majority of penguins will appear against snow. But like Yoav mentioned, there are specific types of camels that exist in the Gobi Desert that might actually exist or be present in front of a background that has snow. And there are also rare and mostly fictional penguins that exist on sand backgrounds. So in this setting, our X is the image pixels, Y is whether it has a penguin, the image has a penguin or a camel, and Z here, the nuisance, is the image background. And the image background is affected by which country we're sampling the data from. Again, in this setting, if I have a function that is naive, that like takes existing data sets where penguins on snow and camels on sand are overrepresented, then it might learn to a mapping between snow and penguin and sand and a camel. The next type of coupling is invariant representation coupling. And in this style of couplings, people typically posit that there exists some representation, phi of x, such that if I transform my inputs x using this phi, the resulting features have a very stable relationship with the label that we care about, y. So the DAG here shows that I have my x and y again, but it shows these zc and zs, and these Z and ZS are not gray, they're white because they're not even observed at training time, so they're never observed. So ZC represents a causal factor, which for the purpose of kind of like this tutorial, you can think of that as a stable factor, whereas ZS represents a spurious or unstable factor. One example here could be trying to predict lung cancer from X-rays. And again, in that case, X is the X-ray, whereas the different environments are different hospitals that the data sampled from. And Y and X can be correlated through two different ways. The first is through that causal factor, which here is smoking. So the relationship between smoking and lung cancer doesn't really change. It doesn't matter which hospital I'm sampling from. But the other spurious or unstable factor, which is the S, that is the X-ray machine. So X-ray machines might have specific artifacts that vary based on which hospital I'm sampling from. So now that we have a definition of the set of permissible sets, we can start formalizing what is our learning goal. And by learning goal here, I mean what kind of risk or loss should we be trying to minimize. And the first sort of relatively obvious thing is that in distribution, notions of risk are insufficient. And by that, I mean these are notions of loss or risk that minimize some average or expectation over the observed training data. Obviously, these will do well on the training data, but it's unclear why would they do well on out of distribution. So our new goal is going to be that we need to reason about a set of risks, and that's the bold R. And the set is all the losses that correspond to all the distributions that exist in our coupling. And the problem is that dealing with these sets of risks might be a little bit unruly or not, at least not convenient. So a lot of times what people will do is that they will aggregate this set of risks using a risk aggregation function that takes us from the set of risks and maps us onto a scalar that summarizes what is the general loss of a specific function h, for example. The important thing to keep in mind is that these aggregations might lead to trade-offs. So we're not guaranteed to be strictly optimal with respect to every one of the distributions that exists in our coupling. So these trade-offs might just be inevitable. I'll go through three types of aggregation, and the first type here is the minimax aggregation, which aggregates the risk by looking at the loss over the worst performing distribution. The nice thing about this is that it gives us an upper bound on all the risks in our coupling, but in minimizing the worst risk, this aggregation might become very sensitive to outlying distributions. And another way of thinking about this is that it might lead to suboptimal performance on distributions that are not worst case, they're not the worst risk distributions. One example of this type of aggregation was used by Madre and collaborators in order to induce robustness to adversarial shifts. The second type of aggregation is quantile aggregation, and this was suggested by Eastwood and collaborators. And you can think of this as a relaxation of the minimax aggregation. So it kind of ignores the worst performing test distributions, and the way it does that is so it'll take this form, and the way it does it is it will look still at the worst case performance, it looks at the worst case distribution, but it's not looking at the worst case over the entire coupling, it is looking at a subset of this coupling, and the subset is defined by all the distributions that have a risk that is smaller than some threshold. How do we get this threshold? We basically look at the distribution of all the risks, and then we look at the CDF, and we look at the quantile, like some top quantile of risk, and we set that as our threshold. The nice thing about this is that it is less affected by outlier populations. The not so nice thing about this is that the distributions that you're cutting out, the distributions that you're throwing out, the ones that have the worst risk, these might correspond to underrepresented populations that we want to make sure that we're fair or we're treating fairly. So this type of aggregation might induce unfairness or unfair models by some definitions of unfairness. Finally, there's the weighted averaging, which does not ignore any extrema. Instead, it incorporates the relative importance of each distribution in our coupling by weighting each distribution using some weighting function Q. So aggregation proceeds by taking the weighted sum over all the losses in our coupling. Now, the nice thing about this is it does not completely ignore any particular test distribution, but the downside here is that it does require us to get a principled way to get this kind of weighting function. One example here is predicting cell types from flow cytometry data, which was work that was done by Blanchard and collaborators. So in this setting, the task is to predict the type of cells. For example, we might be interested in predicting whether or not the cell is a lymphocyte, and lymphocytes are important, for example, to fight certain types of cancers. And each blood draw from a single patient gives us an entire distribution over cells. In other words, each patient corresponds to a distribution over X and Y, where X are the cell characteristics and Y is the label of is this a lymphocyte or not. But we have data from many different patients. Each induces a different distribution over X and Y. So one reasonable thing here to do is to define an empirical distribution over these patient distributions, and that would be our QE in this setting. To give you a quick recap of where we're at, suppose we have some training data sampled from some p-train. In general, we can allow the test distribution to be whatever. But almost all work will limit the set of permissible shifts to be something in a meaningful way. In this tutorial, we will consider shifts with respect to structural components of distributions, and the test set must come from this structured set or the coupling. Now, if we look at the risks, how are we going to define what's a good function, what's not a good function? If you look at this, like the higher, the redder the point is, the more risk it has. And we have here two possible functions, h and g. The top function h does relatively poorly on the training data, but like all the test distribution, or a lot of the test distributions, it performs really well on them. Whereas the bottom function, which is g, it does well on the training data, but it kind of does really poorly on some of the test sets. So how do we pick between those two functions? That will depend on which aggregation, risk aggregation function we use. For example, if we use the minimax aggregation, that will favor the top function, function h, because it gives us a lower risk in the worst case. So now, how do we use these formalisms for better learning? That is something that Aahlad will tell us.
Sorry. All right. Thanks, Maggie. For this part, I will take you all through a few techniques to achieve OOD generalization, along with listing the associated guarantees that come with these techniques. After me, Yoav will take over and really dive into why models depend on spurious correlations from a mechanistic perspective. All right. To start off, let's dissect how ERM can yield poor OOD predictors. So the idea is ERM minimizes ID risk, as Maggie pointed out. This would be minimizing your training distribution risk with respect to a hypothesis class of choice. The problem here is that when you learn the optimal predictor, which in this case will be the conditional distribution of y given x, for the training distribution, you might fail somewhere else in your coupling. So let's see why that might be the case. So we'll take Maggie's example here. you have different doctors with different writing styles seeing the patients with different disease prevalences. So the yellow doctor, who is Dr. Bob, uses phrases like gentleman and sees people who have low blood pressure. This is a correlation that the model can use. So formally, this was the coupling graph that Maggie used. To show you exactly what changes between the training and other distributions in your coupling, I've highlighted the part, unstable part in red here. So your joint distribution over your label, inputs and nuisances, is split in, factorized into a stable distribution over marginal distribution of the label, a stable conditional distribution of x given y comma z, but an unstable relationship between the nuisance writing style z and the label y. So reading off from the dependencies as implied by this graph, we see that when there is a correlation between z and y, even after conditioning on x, this correlation remains. So, and your model, optimal model for the training data can pick this up. Now, if you take this optimal model and switch to a test distribution where the relationship between z and y is different, you can fail worse than random chance. So what can we do about this? Our model is picking up on some nuisance features, and we want to make this not be the case. So let's go back to the objective. So we have three paths that we can change here. We can change the architecture. We can change the distribution with which we're taking the expectations and averaging the loss over, or we can change the loss function itself. You could change the architecture. The property that you want would be your architecture is invariant to the nuisance in your coupling. So in this case, I'm giving you an example of rotated MNIST, where rotation angle of your digit is spuriously correlated with the label. So if you build a rotation invariant architecture, if you train a rotation invariant architecture for this data, your architecture will ignore the rotation and you will get good OOD predictions. But the problem is it's not always clear how you would build these architectures that are invariant to nuisances. For example, if I told you the nuisance is a writing style, it's unclear how you would build an architecture that is invariant to writing style. So we'll focus on the other two ways to modify this objective. So to modify the distribution with which we're averaging, with respect to which we're averaging, we can look at techniques like weighting or balancing, or we can modify the inputs via data augmentations. And to modify the loss function, we can look at invariance or independence penalties, or modify how the model is used in the loss function. I will talk about a few of these techniques in the coming slides. All right, so let's go back to the clinical notes example, but I'll add a little extra node for a simplifying assumption. So specifically, we will ask for there to be some physiological information that is stably related to the label across all members of your coupling. So to rewrite the factorization we saw earlier, you have a marginal distribution y, you have an unstable relationship between the z, between the nuisance z and the label y, and two more stable factors, which are the relationship between the physiological information x star and y, and the stable relationship between your medical note and the physiological information and the nuisance. All right. So if I told you that the physiological information predicts the label stably across environments, our goal will be to use only that information. But we might not always know how to get this physiological information out of the medical note cleanly. So we do not see X star in our training data. One way we can go around this problem is to say there's only two possible ways X can predict Y. One is through the physiological information. The other is through the nuisance. So let's remove the nuisance label correlation and see whether we can get guarantees. So specifically, we'll define this unconfounded distribution where Y and Z are independent. All right. So this corresponds to removing that edge between Z and Y. So in this new unconfounded distribution, if you assume that there exists some function that extracts the physiological information from the medical note, you don't need to know this function, it just needs to exist. In that case, predicting from the input, the medical note, is equivalent to predicting from physiological information. This was shown by Makar et al. And if you take this conditional distribution from the unconfounded distribution, you also achieve this extra property of risk invariance. The idea is that if you use this predictor, regardless of which member of the coupling that you're in, so regardless of the shift in your unstable relationship, you'll have the same risk. Now, this is intuitively appealing because if you see low error on your unconfounded distribution, then you're guaranteed to have low error elsewhere in your coupling as well. But as we remember, we don't exactly know how to aggregate risk without a choice. In this particular case, it turns out that choosing this best risk invariant predictor also simultaneously gives you minimax optimality over this coupling. So regardless of the shift that is possible when you follow this particular graph, you will be guarded against some worst case performance. All right. So how do we do this? I just told you a distribution exists, and then if you use that distribution, then you'll get good predictions. I didn't tell you how to get it. So in this exact setting, we can do this by using importance weights. So you take your training data and weight every sample by the ratio of the marginal distribution of y divided by the conditional distribution of y given c. That breaks the nuisance label relationship. And this is something, this weight is something you can estimate in your training data set. Once you have this weight, all you need to do is run a weighted ARM training procedure. This corresponds to using computing expectations with respect to your training data, but assigning a weight for every sample that corresponds to y, p train of y over p train of y given z. All right. So this is not the only way to construct unconfounded distributions. There's another way, and I'll talk you through it now. One example is you can just make every doctor write a medical note for every patient. So we'll ask Dr. Alice and Dr. Bob to switch patients and write the corresponding notes for them. So this will be denoted by putting in the nuisance in parentheticals after your medical note, X. This is often called counterfactual data. There are many different versions of this. But for now, all you need to know is that if you are able to get this data set, you're guaranteed to have the label and the nuisance be independent, because for every patient, you have every possible writing style. And then the loss minimization for this particular technique will be just to counterfactually augment your training data set and then minimize expected risk with respect to this counterfactual data. I'll give you a very specific example in image recognition for this. This is the data set with wildlife camera traps, where animals in the foreground are spuriously correlated with the background. So a solution here would be to change the background itself. So this was done in Gao et al. By using a segmenter model to segment out the foreground and then paste it onto a different background. So in this case, you're segmenting out the camel and then pasting it onto a grassland background instead of a desert background. All right. Okay. So I told you we made a simplifying assumption. And the simplifying assumption was the label only shows up in physiological information in the clinical note in X. However, writing style could also affect how the physiological information is presented. For example, an experienced care provider may not include all the physiological information, while an experienced provider may provide only the relevant physiological information. So we can't make this, we can't make sure that X star is not connected to Z anymore, so we need to generalize this coupling to this nuisance varying coupling. So rewriting the factorization, again, you have a marginal distribution that is stable. You have a shifting Z given Y relationship and a stable X given Y comma Z relationship. So these graphs are pretty similar. So let's try to apply the weighting solution that we did before. So let's assume I gave you this unconfounded distribution, P cert, where Y and Z are independent. All you have to do is run ERM on it. Let's see if this works. I'll give you an example. So it's very simple. You have a binary label. I'm going to define a nuisance, scalar nuisance, which is a Gaussian random variable with the mean set to AY. And A can change across environments. So that's where the spurious correlation comes from. And then you have your covariates, which are two-dimensional. The first one is Gaussian distributed with a mean Y plus C. The second coordinate is Gaussian distributed with Y minus C. And the variances are different. So if I set A to 0, I have Y is independent of Z. And I can build a classifier in this distribution. So this is a simulation from this example. Looks like we're getting 100% accuracy, which is very good. Okay, I'm going to take this classifier now and then evaluate it on this distribution with A set to 1. And it looks something like this. So your classifier that achieved 100% accuracy when there is no correlation suddenly is at 50% accuracy. So what is happening here? Formally, the trouble is predicting from X in this family uses a non-equal weighting of the two coordinates. So if B is greater than A, due to the second coordinate having much lower variance than the first coordinate, your prediction still relies on a function of the nuisance. This dependence can be characterized as a lack of equality between predicting from X only and predicting from X and Z, so which can be formally stated as a conditional dependence statement. So what's happening is you broke the nuisance label relationship by using some importance weighting or counterfactual trick. And then you condition on Z because conditioned on X because you're predicting from X. And then you reintroduce the dependence. So some of you might have already noticed this. There is a way out of this situation. You just need to take an equal combination of the two coordinates. And then Z cancels out and you only have a stable function of Y and some noise. Okay. For this stable-looking predictor, it holds that even after you condition on it, there is no dependence between Y and Z. We can turn this characterization into a property that we can implement. So specifically, you're going to use a representation, phi of X, such that conditioning on it does not reintroduce the dependence that we broke in the unconfounded data. So this becomes the node algorithm. You first produce an estimate of the unconfounded distribution, and then you are going to learn representations that are uncorrelating in the sense that they do not introduce correlation between Y and Z. Implementing this is, you do it in the following way. You have a minimization over representations and a function on top of this, which under the constraint that when you condition on this representation, the dependence is not reintroduced. This nuisance varying families allow for these kinds of mixing variables where like you can have features that are both label and nuisance dependent. So risk invariance may not always give you good predictors. But you're doing this particular kind of independence constraint is guaranteed to improve over risk invariance for certain sets of nuisance varying couplings. All right, so quick takeaways. So this balanced training where you break the relationship between the label and the nuisance does yield the best risk invariant predictor. But if you generalize this to a coupling where you cannot extract the X star from X, then balancing is provably problematic. Enforcing the conditional independence with a representation mitigates this problem if you can solve the objective. All right, so that's one way you can build ORD generalization in this graph. This graph tells us a few other things, so let's try to employ those other properties and see if we can achieve ORD generalization. So specifically, you can read off a conditional independence that holds for this X star stable predictor. So specifically, the independence is that X star is independent of the nuisance when you condition on the label. So if you have this property, then I can impose this property on a representation that I'm learning. And this objective corresponds to just building a predictor on top of this representation that you've imposed the conditional independence on. Okay, so let's write down the exact objective. So we're going to have a model that takes in a representation and a function on top of the representation. And we're going to minimize empirical risk for this overall model while imposing a dependence, a penalty to control how far the distribution of the representation can change when you condition on different values of the nuisance. So here D is some divergence between distributions, and if this is 0, then you know that phi of x is independent of z given y. So there's many different versions of this particular penalty that were implemented in practice. We'll look at one of them, specifically invariant risk minimization. So the coupling now changes. We are now in invariant representation coupling. So you have two unobserved features. One is the causal feature, which is smoking. Your label is lung cancer here. And you have a spurious feature that is the chest X-ray scanner. Because different hospitals use different chest X-ray scanners for people with lung cancer or not, the scanner type acts as a spurious feature. So the feature ZS, which is unobserved, is correlated differently with the label depending on which hospital you're in. So reading of the conditional independence here, the label is independent of the environment if you condition only on the causal feature that is smoking. So that is ZS. If you additionally condition on the causal feature is ZC. If you additionally condition on ZS, you will introduce dependence between environment and label, which is something that leads to poor OID performance. Okay, so how do we fix this problem? We're going to let our model produce some scalar output, some probability of y equals 1 given x. We will then impose that this model have produced the same conditional expectation over y, whether you're in environment E1 or E2. And then Aahlad et al. Produce an algorithm to do this, which looks something like this, which is minimizing empirical risk while you penalize the gradient norm of the loss with respect to a temperature parameter that multiplies your model. So this feels like a big jump, so let's walk through it. First, we'll write down a stronger version of the invariance statement that we just saw. So if you want your conditional expectation to be the same across two different distributions, you can achieve this by forcing your model to be calibrated. So what does calibration mean? If my model tells me the probability of y equals 1 is alpha, then for the samples for which my model tells me that, the actual expectation should also be alpha. And this needs to hold for every environment in your that you know of. Okay, so this is a proof from Wald et al. We'll show that IRM V1, the gradient norm penalty, is a relaxation of this multi-domain calibration constraint. Okay, so let's carefully walk through this. It's okay if you zone out a little bit because it's a lot of math. So if multi-domain calibration holds, that means that taking the conditional expectation of y given what your model probability is should be equal to what the model probability is. So our model probability here is alpha. You can move your alpha to the left-hand side and get a conditional expectation of a difference. As this holds for every alpha, we can also expand out the definition of conditional expectation to check that when the condition event holds, y minus phi of x is uncorrelated with phi of x. Okay, so this in turn gives you the ability to test for whether phi of x and y minus phi of x are independent of each other. So you can use a test function that is any measurable function and take the expectation to check the correlation, including the identity function. So if you take the identity function, you get something that looks like this, which is exactly the gradient of mean squared risk evaluated at the temperature parameter W set to 1. This is the IRM constraint. So this summary of the slide is that model calibration gives you the IRM V1 penalty being set to 0. These kinds of notions are also related to the idea of low-degree multi-calibration. If you use different simple functions, you can check this dependence to a certain extent. All right, so to summarize, if you have a linear representation and your inputs x are an invertible transformation of your causal and spurious features, you're guaranteed invariance with the IRM objective if there are enough diverse environments. So you can't just observe one environment in your training data, you need to observe multiple. So Chen et al. Show that the number of environments you need scales with the dimension of the spurious features, so which is not exactly something you observe in your data, because you were only told at the beginning of this, when you assume this coupling, that you have data from different environments. So the assumptions are a little bit separate. Finally, if your spurious feature can get really large in magnitude, invariant risk minimization is guaranteed to give you a minimax predictor, and where this maximum is over all possible distributions in the invariant representation coupling. So again, this guards you against worst case performance regardless of where this predictor is used in the coupling. All right, so finally coming to the third kind of coupling we saw earlier, this is subpopulation shift, where your mixture proportions for different subpopulations, denoted here by lambda in red, change across environments. Your subpopulations themselves are fixed, but the mixture coefficients change. So the example that Maggie had shown you earlier was you have different hospitals where men and women have different prevalence of being sick or healthy. So if you pay attention to hospital B here, you'll see that 85% of the data have sick men and healthy women. So this means if I build an ERM predictor on hospital B, I'm going to end up predicting health status based on gender. And this is problematic because when I switch to hospital A, where the remaining subpopulations are much smaller, much larger than in hospital B, my error now explodes. Okay, so how do we fix this? One way to do it is to ensure that no subpopulation has high error. You can achieve this by the group DRO objective that's been developed by Sagawa, Oren, and Hu et al. In different papers. The idea is to take your minimization over the worst risk subpopulation. So this turns out to be equivalent to doing a minimax aggregation over all the members of your coupling. This is not hard to see because if you take a maximum over all weightings of the subpopulation, that maximum will equal to the risk of the worst subpopulation. And so these two objectives are equal. All right, so we have a few methods that I covered. Do they always work? Gigul, Rajani, and Lopez evaluated a few of these methods, specifically comparing IRM, ERM, DRO, and some independence objectives like Coral. They found that none of these methods significantly outperform ERM consistently. Okay. So I'll now hand it over to Yoav to dive deeper into these kinds of issues that happen in practice and try to explain why models really rely on spurious correlations. Thank you.
Okay. Thank you, Aahlad. And now I will move on to the second part of this second part. And what we'll begin now is a series of 3 little sections. At each, we'll cover a certain gap, okay, that underlie the results that Aahlad just showed us, and maybe underlie also the slow adoption of out-of-distribution generalization methods in real-world problems. So first, we will ask if the solutions we just saw tackle the correct problem. Okay? Then we will discuss some assumptions we made about the auxiliary data that we kind of assumed we have in all of these solutions, and the graph structures that Maggie talked about in the first part. So we will start off by asking, why do models really learn spurious correlations? Is it the reasons that we kind of depicted so far? So part 1 emphasized these statistical reasons. That is, that the conditional distribution of y given x changes across our different environments. And that leads to a higher loss for our model, right? Then we were able to tackle this thing this problem with an adjusted learning rule, like Aahlad showed us a few examples of those. But it turns out that besides this type of statistical reason, there's a geometry that plays a large role. So to understand exactly what this means, let's consider an example of distinguishing cows from penguins, okay? Intuitively, for the sake of the argument, if we disregard factors like occlusion or image quality in this problem, it should be possible to distinguish these two animals regardless of the backgrounds of the image, as illustrated here. I think we can all distinguish the cows and the penguins. So what exactly do you mean by geometry playing a role here? We mean that optimizing the network equates with, but it turns out that models actually still rely on these background features, even though they are not necessary for prediction. Okay, so let's see a toy problem example that illustrates the dependence of trained models on backgrounds, even when they are not necessary for prediction. So we take a set of distributions that's been considered in many, many works on related topics, like Rosenfeldahl, Segawa et al. And the parameter phi flips the sign of the nuisance and flips the sign of the label with some probability. Okay, so we get some disagreement probability between the label and the nuisance. And the features are simply consistent of labels multiplied by some stable feature, mu star, which is our stable feature that we talked about earlier, and the nuisance or spurious feature is mu z, okay, which is multiplied by the possibly flipped label z with additional noise. So the plot kind of depicts what goes on in this setting. So it's the projection of x on some different directions. On the left, there is the projection on the stable feature on the x-axis, which kind of depicts the type of animal we are interested in. So it's either a penguin or a cow. And on the y-axis, the projection is with the nuisance factor, which is a background, either snow or grass. On the right, we just have some additional projections that are noisy features, the added noise that we had. So the correlation between mu z and y creates this type of majority group where z and y agree on their signs. So here, theta e is the probability that these two things, these y and z agree. And when it's high, for instance, 0.9, like here, we get a large majority group where z equals y. And it also creates a minority group where z is not equal to y, and this is pretty much, we'll call that the shortcut group. So, okay. So now, adding the assumption that the stable feature is orthogonal to the nuisance, and also that it is noiseless, so as I said, we're barring anything like occlusion and things like that, we see that there is really no shift in the conditional distribution. So all of the statistical reasons we laid out in the first part and the second part do not play a direct role here, okay? Instead, we'll be seeing effects due to finite samples, right? That's the kicker of the next part. So what happens is that the dependence, that if we have a model that depends on the spurious feature of mu z, it will induce an error in each and every environment. So if we have infinite data and we minimize the expected risk, we assume we expect not to learn that feature. So if we take this problem and we train a two-layer neural network on a set where theta e equals 0.9, then what we see is that training accuracy, marked by solid lines here, goes up to 100%. These are the solid lines of both colors. And what that means is that we interpolate our training data. That is, we fit it perfectly. So the dashed line shows accuracy in a test set from the same distribution. And what we see is that the gap in accuracies between the minority and the majority group is very large. These are the two different colors in the dashed lines. So this can only be a result of the classifier learning to use the nuisance, mu z. Okay? So what we conclude is that using z here leads to a gap that is larger than 50% between the groups. And we conclude that pretty much a network that's trained with stochastic gradient descent, in this example, results in overfitting. Okay? So overfitting here means that there is some generalization error in the training distributions. And what will happen under the distribution shifts that we talked about when theta changes is that this minority group we talked about becomes larger. And then the expected error becomes also larger. Okay, so now let's go back to our original question we started out with. We asked, why do models really learn spurious correlations? And it turns out that this can be attributed to the inductive biases of training neural networks with stochastic gradient descent and the logistic loss. So past works on this topic have shown that when trained on separable data, this procedure will tend to learn large margin separators, which translate into a type of simplicity bias, where networks tend to rely on features that are easy to pick up, or like the background we just talked about. In the examples we just discussed, the synthetic one, so Nagarajan and collaborators call this a statistical skew, since it learns solutions that are skewed with respect to the optimal one, which totally ignores the nuisance or the background. So this is mostly a problem when models can interpolate the data, and there are many possible solutions to minimize our risk. So we saw that we get a risk of 0, and there are many possible solutions that achieve that. And among them, training tends to converge to the simplest one. So when we ask, do models really rely on spurious correlations, it may be due to simplicity bias, or it may be to statistical reasons that we mentioned in the first part. But of course, it seems like this is not a purely distinct problem. We can't really attribute it to one versus the other. And it is usually a combination of both that leads us to learn spurious correlations. And perhaps a better way to think about this is that we learn spurious correlations because features or nuisances are predictive of the label. But predictive strength is not merely due to a statistical association. It is also a function of how easy it is for our models to learn these features, to pick them up. So to wrap up the intuition here, simplicity bias is not a problem without considering distribution shifts. It is also true that handling distribution shift almost always has to take implicit biases into account, and because an implicit bias is baked into most learning methods, and often because the multiplicity of possible optimal solutions comes from following common practice in machine learning, where we train high-capacity models. But now the key point I was trying to make is that the methods that Aahlad covered did not take geometric principles into account, did not really account for these implicit biases. They only accounted for the statistical ones. And the key question we'll answer in this part of the tutorial, where we cover some works that worked on this problem, is how can we control for the implicit bias of models, for this implicit bias. And we'll first ask whether the methods we already saw actually control for them already. So to start answering the second question and see whether the methods we've seen so far solve the implicit bias problem, and we get it for free. So let's start with importance weighting, a method that Aahlad covered. So if we follow the recipe that Aahlad showed us, it should upweight the loss of the minority group. That's what would fall out of that. Here we depict that by just making the points in the minority group larger. But when a data set is separable, like we talked about in the cow and penguin example, so reweighting doesn't really affect what is the maximum margin separator, or what is the simplest model that solved the problem. And this type of implicit bias will not be addressed. And Zhai and collaborators show results about this type of generalized version of reweighting, a much more general thing that I've shown here, and give an intuition to explain how these things can be ineffective when training high-capacity models. So the other family of solutions we saw was invariance penalties. And here many works have also pointed out that empirical findings about inefficacy of these solutions when applied to high-capacity models. So this here is an example from the fairness literature, where these invariance penalties are quite popular. And on the left, there is a plot where the distribution train and test error on the Waterbirds data set as we train a larger and larger model. So the training error drops to 0, and the model interpolates the data, while the test error of the training distribution displays this well-known double descent behavior, where we take over-parameterized models and our loss still kind of drops, and we get good performance on our test set. But this is all in distribution. But the penalty that the authors use here, it's called min-diff, for the sake of just completeness, that the goal of this penalty is to reduce something called the the false negative rate gap, the FNR gap, which is plotted on the right-hand side for varying strength of the penalty, which are denoted by lambda. And what we see is that for interpolating models on the right, whenever we cross the overparameterization threshold, the regularizer does not affect implicit bias of the model. So pretty much all of the different different penalty strengths we include result in the same fairness penalty and do not really affect the solutions. So what we conclude is that this strategy is not effective in controlling for implicit biases. So returning again to our question, we rule out the possibility that the methods we've seen already solve this problem. But researchers did come up with alternative ways to control for implicit biases. For instance, instead of importance weighting that we discussed earlier, people have studied importance tempering, where instead of multiplying the loss by a weight, we multiply the logit by this weight, and adjust the logit additively is also something that has been suggested. And Sagawa et al. Also showed that to solve group DRO, another method that Aahlad mentioned earlier, this heavy regularization or early stopping is required. Sorry. So these adjustments mostly try to correct the implicit bias due to interpolation or due to overfitting our data. But there's also works that claim that often this is a better idea just to avoid interpolation altogether. So we should not overfit our data. And a little deep dive here, which I'll do very quickly, is to look at our synthetic example from earlier, which is a pretty useful model for learning shortcuts in real data, and it's a pretty representative example. And if we look at the problem of training a linear predictor, then it turns out we can reason mathematically about the dependence of models that interpolate the data, that separate the data, about their dependence on the spurious features. So apparently you could write this nice optimization problem where the objective is just the dependence on the spurious features. So this is the projection of W on the stable feature over its projection on the spurious feature, and this can be related directly to the generalization error of this W under distribution shift. And we then constrain this to W to be an interpolating model, which means that it separates the data with some margin gamma, whatever margin it is. So, and then what it turns out you could do, which is a nice little mathematical fact, you could obtain lower bounds on this problem with convex duality. And then you could show that any interpolating model, and I mean any interpolating model because the value of gamma here is arbitrary, we could show lower bound for any value of gamma, which means any implicit bias that you may think of. Pretty much, so any of these interpolating methods will have large weights on the spurious features, mu z. So what that paper also suggests, that it suggests another algorithm that does not interpolate the data that provably has better bounds on the dependence on the spurious feature. So it is provably better on this type of toy problem. But it is motivated by real works on real methods that also do not interpolate the data. So one set of methods that avoids interpolation and achieves very good out-of-distribution generalization is this method by Kirichenko et al. It's called deep feature reweighting, and there are other types of methods that will follow the same spirit, and the spirit is to do a two-stage learning procedure, where we first split the data into two sets, the training set and the validation set. And the first set, what Kirichenko and collaborators do, is that they simply train an empirical risk minimization on the training data set. And then what they show empirically is that on several spurious correlations benchmarks, the stage of learning a representation, learns a representation, pretty much the first stage, learns a representation that is rich enough such that in the second stage we can just freeze the entire network, everything but the last layer, and then use any of our lovely robustness methods that Aahlad showed us just by fine-tuning the last layer. And this will actually be sufficient in order to learn a robust classifier. what happens in terms of interpolation is that maybe we overfitted our first large data set, but then we kind of just fitted a small model that is on the linear layer, and we didn't interpolate the other part of our data set. So that's the first way of avoiding interpolation. Another way that's quite popular in terms of the group DRO solutions, where we want to achieve robustness across different groups, is to subsample our data. So we said that importance weighting is not a viable solution with interpolating methods. So instead of importance weighting, what we could do is to do rejection sampling. So here we just depict that by throwing away some points in order to make the minority and the majority groups of the same size. And then if we learn the best predictor on this distribution, we're guaranteed to learn an unbiased interpolator, or an unbiased model. And a key thing here about interpolation is that maybe we interpolated the subsample data, but we did not interpolate our entire biased data. And that's how we avoided this kind of technical mishap. Okay, so that was part 2, was our most technical part. And now we continue the tutorial with part 3, which, if you remember, I told you that we'll go through 3 challenges that are inhibiting the application of OOD methods in the real world. And in this part, I will first go through challenge that relates to auxiliary data. And then we will discuss the challenges with the graph, and that will be up to Maggie. So, okay. So going into our pretty much our challenges, what did the methods we study so far require in terms of our assumptions? So first thing they required is auxiliary data, right? We said that we had environments, nuisances, groups. All of these needed to come from somewhere, and someone needed to annotate them. So whether these are different hospitals or different demographics, etc. These are not always available or easy to collect or easy to reason about. And there are 2 challenges that in terms of this of obtaining this data. First is that the annotation can be very costly or unavailable. So an example for that is you could think about social determinants of health. What that means, often in health, we care about subgroups that are defined by different, social properties. And some of these are widely available, like data about income or about places of living. But some of them are harder to collect. So for instance, data about transportation or about mental health is very hard to collect, and these annotations are much more costly. So this is challenging, right? How do we get group annotations for this? And the second thing is identifying what thing will shift. So if I think I might have some spurious correlation with a nuisance in my data, I need to know what that nuisance is, and it's really unclear how to do that. Here, for instance, this is a chest X-ray example where the nuisance could be either the scanner type that we talked about earlier, could be something like the time of day because certain types of patients get scanned at different times, or it could also be some technician markups that people observe that also spuriously correlate in different papers with conditions in chest X-rays. Okay. So people thought hard about ways to achieve robustness without this auxiliary data, and here is one example, popular example of a method for this task. So the example I'll go through very quickly is just train twice by Ziu et al. And if we go back to our synthetic example of the cows and the penguins, their method will pretty much proceed as follows. It will first just train a model with empirical risk minimization, as we talked about. We'll try to minimize our loss, and we'll get our ERM predictions. This will be perhaps the ERM classifier learned here. And then in the next stage, what we'll do is we'll take another data set, or a held-out data set, validation data set, and we'll look at our mistakes, the problems, the points where our first model predicted wrongly. And then we'll take these mistakes and we'll upweight them, again, by enlarging the dots and the triangles here. So once we upweight them, we just train another weighted risk minimization, and what will happen is here that we'll learn this weighted classifier, which is tilted more towards the correct direction of relying just on the stable feature. So, so the reason, of course, this happens is that reweighting, this function, this method, mimics the reweighting procedure that Aahlad talked about, and because the mistakes corresponded to the minority groups that we talked about earlier, and once we upweight them, we get something similar to the solution we saw earlier. So, sorry. So there are several methods where they're similar in spirit, like EEL, like Krieger et al., which do the parallel, but instead of reweighting, they use these invariance penalties. And maybe an even more complex and kind of elaborate method is a recent work by Arafin and collaborators, which use this self-supervised method to learn these representations, and then they they cluster these representations to obtain groups and run the group DRO algorithm we talked about earlier on these obtained groups. So the thing is that I think is very crucial to notice here is that we didn't talk about what is the underlying assumptions. Where do you obtain this data from? And the underlying assumption here is quite complex. We assumed that pretty much all of the mistakes that, for something like JTT or just train twice, found in the first phase are due to reliance on the shortcut. And that's a pretty hard assumption. That has several caveats. One is that what if some mistakes are not due to the shortcut? Like when you have large data that is beyond this kind of synthetic example, it's hard to believe that everything will be just due to the shortcut. For instance, what if we have label noise? And label noise here will be flipping these triangles and circles around. Then label noise will actually make our weighted ERM solution tilt to the wrong direction of the unstable feature. Another thing, of course, is that these methods, they include an assumption about the model. They're assuming something about what the model will learn, right? So this is like, for instance, assuming that the self-supervised method that I've just mentioned by Arafin et al. Will learn a representation that will correspond to the groups. And in today's machine learning literature, it is very hard for us to reason about anything that a model will learn or know what exactly it will pick up on. So, okay, where can we go forward from here? This is a very tough problem. How can we get methods that rely on more realistic assumptions? So, one idea that is maybe a small step towards that direction is the idea of semantic corruptions. So these are transformations that corrupt the label. So an example, if we have this cardiomegaly detection problem with chest x-rays, we want to detect cardiomegaly from chest x-rays. What we know, as professionals know, is that in order to detect this, the machine or a doctor must observe the heart. And here we have an example where the label is cardiomegaly, and let's say that the nuisance or the spurious feature is with the scanner type that is taking this X-ray image. So the intuition is that if we occlude the heart area from this image, then any other feature that is left in the image is actually a nuisance. It's something that we do not want to depend on. Okay? So if we occlude this thing, we are left merely with nuisances. But the nice thing is that the information about scanner type is actually present throughout all of the pixels of the image. So I could tell what is the scanner type, or a machine could tell what is scanner type by just looking at the edges of the image. So the type of advantage here is that we maybe did not know up in advance that our nuisance is scanner type, but we were able to somehow get this image that captures what is the nuisance, what is the spurious feature. So the method, pretty much what it does, the method that's suggested by Puli et al., is that to use this corrupted image now as your entire Z that we talked about earlier, and just use the methods we talked about regarding reweighting. We learned this p-train of y given z with standard machine learning algorithms, and use this to reweight our samples. Okay, And this type of idea can be applied across modalities. So in text, they showed if you could flip the order of words to destroy semantics and certain tasks, and other types of vision problems and other types of corruptions. Okay, but again, we still have an underlying assumption. And the underlying assumption was, of course, we have access to some kind of a transformation of the image or the text that corrupts the label Y, and also maintains the nuisance Z. So this is a pretty strong assumption still, and it's definitely, we don't know if it's applicable across real-world settings, and people haven't maybe discovered real nuisances with it. So, takeaways about this part. So we have challenges of obtaining auxiliary data with groups. There are regarding annotation cost, and about identifying what is it that will shift. And existing methods, one thing that we're kind of suggesting towards progress in this field is that existing methods should clearly state what is it that they assume about the data, or that leads to identifying the auxiliary data that we need. And there is a lot of potential here for future work about different methods that can yield auxiliary data and different assumptions. So now I will hand this over to Maggie to present the other type of gap we have towards safe deployment. Thanks.
All right, so the other gap that we'll talk about now is this gap of we need to know what is the knowledge graph. Like all the methods that we talked about, we need to know what the knowledge graph is. But the reality is there's a lot of existing work and there's a lot of papers out there that don't really talk about the graph of knowledge or anything. They're just, these methods exist, and just because they ignore the graph doesn't mean that their results are worse. For example, you see all these papers, and they have like really good out-of-distribution performance. You see that their empirical results are such that the suggested model does really well, and the benchmarks do relatively poorly. So do we really need to know anything about the graph? The upshot of what I'm going to say in the next couple of slides is that there is a downside to not knowing the graph, and often the case, the mismatch between the graph implied by the data sets that are used and the graph that is assumed by the method leads to misleading results. One of the signs of this mismatch and the importance or the consequences of it is that this good performance that we see in papers often does not hold under slight perturbations of the benchmarks. So for example, in healthcare tasks, Zhang and collaborators found that the ERM, so a model that does not do anything about OOD generalization, performs better or as well as methods that were specifically designed for out-of-distribution generalization. More recently, specifically in this NeurIPS, there is a paper by Nassel and Hart that explicitly tried to investigate this inconsistency in results. And in their investigation, they looked at different benchmarks, or specifically benchmark data, and I'm going to plot that on the x-axis, and the out-of-distribution accuracy, and that's going to go on the y-axis. And they compared methods that use all the features existing in the data set to make a prediction to methods that only used stable features, stable as identified by some OOD-specific approach. And here, the notion of stability that they used was based on causality. But you should check out the paper for more details in the poster. In addition to those two sets of models, they also looked at models that are just predict a constant. And what they found is that the empirical risk minimizer does as well as, or in a lot of cases, better than the methods that were explicitly designed for this out-of-distribution generalization. In similar work, Bell and collaborators looked at the correlation between the performance of different models on different data sets. So what you're looking at here is the heat map of this correlation. And the upshot or the conclusion from this plot is that there is no high correlation between the different methods, which is to say two methods, one method can perform really well on one data set, but really poorly on another data set, and it's not obvious what the correlations are here. As I alluded to earlier, one of the reasons that this happens, that this inconsistency in result happens, is because of the mismatch between the assumptions and the graphs. So if a set of authors kind of set out to write a paper and they have a proposed method, maybe they don't explicitly state it, but this proposed method might implicitly or explicitly assume or require specific knowledge graphs or causal or directed acyclic graphs. But then they take their proposed approach and compare it to comparator models that do not assume the same graph. And in addition to that, they will run their analysis on benchmark data that typically conforms to the graph that is implied by their proposed method, but not the comparator method. So obviously, like in these settings, it's kind of obvious why one would end up with like really nice conclusions in the paper, but once you kind of move out of the paper, these nice conclusions don't always hold. And one of the reasons why this happens is partially, but not always, because it's not clear what graphs are implied by the benchmarks that exist in general. So for example, there are some benchmarks where they are relatively simple, so it's easy to reconstruct what the underlying graph is. For example, C or colored MNIST. It encodes specific correlations between the color of the digit and the digit itself, and the task here is to predict the digit. So it's nice and simple, and you can fully reconstruct what the underlying graph is. Similarly, with other very popular data sets like Celeb-A, or the Waterbirds data, or the multi-NLI data, they're all simple enough to reconstruct the graph. So the nice thing about these simple structures is that they give us, the simple graphs, data rather, is that they give us a known structure, but they are almost too simple to mimic real shifts that we might be interested in. On the flip side, if we then use very complicated data sets, like some of the data sets in the Wald collection or the table shift collection of data sets, these are more complex, but the problem now becomes that we don't know what are the graphs that are captured by these data sets. So for example, which one of those graphs is implied by which data set, we don't know. Other things that we're not really sure about are the nuisances observed and which subpopulation shifts are allowable within these benchmarks. So looking forward, one area of growth for the community is to agree on best practices that involve clearly specifying the assumed graph when creating new benchmarks and new methods. Another important step forward would be to create realistic benchmarks with tunable graphs that allow us to stress test new methods under varying levels and magnitudes of shifts and under different types of graph. One step in that direction is metashift, where this type of data sets, it allows us to annotate objects and backgrounds and object attributes, and then it allows us to group different examples based on the co-occurrence of annotations. And then combining those groups of rare co-occurrences can allow us to test our approaches under kind of difficult settings. And we can also create a desired graph by creating correlations that we care about. In the last part of the tutorial, we will talk about something that I'm sure a lot of people that are interested in out-of-distribution generalization have heard before, which is, doesn't scale solve all of this? So we'll address whether or not scale, like just increasing the size of the model or a data set, just kind of magically removes the issue of out-of-distribution shift. And we will talk about whether or not this scale increasing leads to better out-of-distribution generalization, if that paradigm breaks, and under what setting it breaks. And in the last part, we will discuss recent work on these kinds of questions and how to mitigate spurious correlations in big foundation models, and how can we leverage the abilities of large generative models to improve their robustness to spurious correlations. Okay. So again, a lot of us have heard this idea that scale is all you need. This has been supported empirically, to be fair, using the notion of accuracy on the line or accuracy on the curve. Okay, something is off with the slide. Accuracy on the line just refers to the fact that correlation between in-distribution and out-of-distribution performance is high. So if a model does really well in distribution, it will do really well out of distribution. So what you see here on this slide is on the x-axis of this plot. The authors, Miller and collaborators, looked at in-distribution accuracy, and the y-axis is the out-of-distribution accuracy. This dashed line, the y is equal to x line, it kind of looks at, it depicts what an ideal model that does equally well in distribution and out of distribution would look like. So that's our hope that good models will lie somewhere on that line. But what they did is they looked at neural networks that were trained from scratch, and that's the kind of blue line that you see here, the dark blue line. And they also looked at a neural network that was pre-trained on a large data set, which is ImageNet. So you can definitely see that there's a correlation between in-distribution accuracy and out-of-distribution accuracy. It's not perfect, but it's a very strong correlation. And not just that, this correlation increases or becomes closer to perfect in settings where the model is bigger, and here bigger means it was trained on more data. So the question here becomes, if I have a model that has really good in-distribution accuracy, what does that tell me about out-of-distribution accuracy? Is it always true that I can assume my out-of-distribution accuracy will be better because my in-distribution accuracy is good? The same paper also showed similar trends that happen on many naturally occurring distribution shifts, and along the same vein, Radford and collaborators found a similar trend for models that learn without direct supervision, like CLIP. So they created shifts where like the main model was trained on images, like real images, but the shifted data set included things like rotated images, or the backgrounds were swapped out, or instead of the true pictures, there were sketches of pictures in the test distribution. And they found similar trends, that the bigger the scale, the better the correlation between the in-distribution and out-of-distribution generalization. The important thing here is that the training data for these kinds of work did not exhibit a spurious correlation or an exploitable shortcut that the model can use for prediction. So we will next go into settings where this trend is weaker or altogether broken. So first thing we notice is that the results are less impressive when the training data has a potential shortcut. So there's work by Liang and collaborators where they look at different subpopulation shifts where at training time the label was more prevalent among a specific subpopulation. For example, they looked at the bird classification data set, which we alluded to earlier, where you want to classify if it's a water bird or a land bird, and the backgrounds are either water and land. So maybe at training time the majority of water birds appear on water backgrounds, and land birds appear on land background, and this creates that exploitable shortcut that the model can learn. Again, here the dashed line would be a model that is fully robust, but the trend that they see is more of a curve rather than accuracy on the line. So definitely it's less impressive, and they found similar trends among other data sets. So the idea here is that in order to gain that nice out-of-distribution accuracy only by scale, you need to scale up to a point where your in-distribution accuracy is really, really high. In other work by Wenzel and collaborators, they showed that they can reproduce this trend of like highly correlated accuracy in distribution is correlated with good accuracy out of distribution, but they were able to recreate it only in some of the data sets that exist, but in other data sets the trend was like completely flipped, or it was like entirely nonsensical. Like there are some of these plots that like don't really show a discernible pattern. So this is to say, these trends that the better your in-distribution accuracy, the better you should expect your out-of-distribution accuracy to be, are just not guaranteed. There are settings in which they fail. In other work by Sanyal and collaborators, they found that things like label noise, which tends to happen a lot in real data sets, can also lead to even negative correlations between the in-distribution and out-of-distribution generalization. So to recap, it looks like maybe plugging or building bigger and bigger models, sometimes that can lead to better out-of-distribution generalization, but it's unclear when that kicks in. And we don't know exactly how to classify benchmarks based on whether or not, or even not just benchmarks, like what are properties of data sets that need to exist for in-distribution accuracy to translate into out-of-distribution accuracy. In the next part of the tutorial, Yoav will show us examples of how scale interacts with spurious correlations by stress testing large models and understanding how these models can be adapted to help mitigate reliance on spurious correlations.
Great. Okay. Thanks very much, Maggie, for the great scanning of this literature. So next, as Maggie said, we will look at the interplay of large-scale and spurious correlations, and we will view two quick insights from very recent work on spurious correlations and large models. And one is about the robustness of zero-shot clip to spurious correlations, and the other is about shortcut learning in context learning. So we saw earlier in the tutorial, but Maggie just talked about it, that zero-shot classification of clip is rather robust to natural distribution shifts. That was a finding from Radford et al. But what Wang and collaborators, presenting their work this week at NeurIPS, what they note is that these observations were made on spurious correlations that exist in ImageNet data. So ImageNet, of course, distinct from the type of data that CLIP was trained on. And it is more plausible that CLIP will latch on to spurious correlations that are prevalent in its own training data, or their own training data. So for instance, in the Lion data set that CLIP uses as a pre-training data. So what the authors did is they took a label data from iNaturalist, which is included in Lion, and they manually labeled backgrounds in images in a way that then they can construct a data set that is very hard, that has very hard pairs of these animal background relationships, where the drop of performance for CLIP is the largest when you switch from an easy background to a hard background. For instance, here is an easy pair is an ice bear on a snow background, while a hard pair is this ice bear on a grass background. And they observe that CLIP actually has a very large drop when you look at these two types of groups. So CLIP shows significant accuracy drops, and some of the pairs of classes and backgrounds that exhibited are shown on the table here on the bottom. Yet besides these significant performance drop, they also, which maybe you've anticipated this performance drop because spurious correlations don't go away, but they've also observed some very interesting things about which models are more robust than others. So it turns out that models trained on ImageNet, so presumably with less pre-training data, show better robustness than CLIPs on this specific problem, on this specific data set. Which alludes to the conclusion that data set size alone is not a deciding factor for robustness. There are other factors. So what they did find, there are several other interesting findings in these papers, and I encourage you to go visit them during this week. So one other finding is that maybe larger models are better than smaller models in their robustness, but mainly that cleaner data or different curated data sets like data comp, which is a pipeline to improve data quality, helps a lot with robustness. And there is a concurrent concurrent tutorial going on now is related about data selection for foundation models, but don't worry, it's all recorded, so you can stay here. So, okay, so moving on. Sorry. So moving on, the second insight that we point about spurious correlations in large models relates to in-context learning. So in-context learning gained a lot of popularity versus its counterpart of in-weight learning, which was the common method before that. And now it's very interesting to ask if we are all using this method of in-context learning where we give a large language model or a different model examples of our task and expect it to solve it for us. How sensitive is this method to spurious correlations? And this was studied by this paper by Tang et al. And what they do is they just construct these simple examples, like here in the image, where the word movie is correlated with positive movie reviews in the in-context learning dataset that they provide for the language model. And what they observed, perhaps somewhat unsurprisingly, is that indeed the in-context learning method will latch onto the shortcuts. So movie will be correlated with positive. And once we remove that correlation in the test dataset, we'll get some errors. So this may be expected, as we said. But the interesting thing is that actually they show that the drop between the accuracy in distribution and out of distribution grows larger as the type of model that you use is also larger. So if you take a very large foundation model, the accuracy drop, which is the y-axis here, so the y-axis here is actually the drop in accuracy between in distribution and out of distribution. You can see that as we go to larger models on the right, it grows as well. So the takeaways from these two examples is that model size increases increases the dependence of shortcut under the in-context learning paradigm, but it reduces sensitivity to spurious features on CLIP. So it does seem like understanding the effect of model size on robustness to spurious correlations in a variety of settings would be a great open question for the community to try and answer a bit more concretely. So to finish this tutorial on a positive note, because we kind of talked about now how large models are still very sensitive to spurious correlations, we'll talk about ways that these large models can actually help us mitigate spurious correlations. And we'll see again 2 quick examples of works that use the abilities of these models to encounter robustness, to achieve robustness. So if we recall part 3, which is ancient history by now, I told you that there are 2 challenges with obtaining auxiliary data, like group annotations and environment annotations. And the first challenge was that annotation can be costly, that it's very hard to get these labels and we need human labor for that. And in recent work at ICML, so Settler and collaborators suggest a very nice way forward that perhaps large models can provide an opportunity to obtain these annotations in a very cheap and easy way. So, assume that we are concerned with a certain attribute, for instance, the background of an image, like we were earlier. We want to know what is the type of background that an image has. And we think maybe it might be spuriously correlated with some object that we are interested in detecting. So their method is very simple. So step 1 is we'll prompt some visual language model, some VLM, to annotate the nuisances, or like they call them confounders, what we call here nuisances. So just so you're not confused by the labels that's going to appear here. And once they ask the VLM to identify that background for them, they will use these pretty much these annotated examples to use any type of OOD robustness method that Aahlad showed us in the second part of the tutorial. So here they used group DRO. And the kind of positive sign for why this method would work is that it turns out what they do is that they show that when you take a larger and larger model, it turns out that it's very, very good at predicting the background of the image, at identifying the background, while it is less good at predicting the object of interest. So here, in some case, it's sort of a double-edged sword, because our models, or large models, were sensitive to spurious correlations. But in that sense, they also predict them very well, so they also allow us to annotate the nuisances or the spurious correlations that we are worried about in greater efficiency. So this is pretty much a sketch of their method. As we described now, we pretty much our human that reasons about what are possible spurious correlations asks the VLM to tag them, and then these go into another method that learns a robust predictor. And they're able to get pretty impressive results on the spurious correlations benchmarks that we talked about. And the nice thing is that if you look at in-context learning on the right-hand side there, so the checkered bars here are the worst group accuracies. So you can see that something like in-context learning is actually not as good as just training a classifier like ERM, but when you use their methods, you actually kind of tap into all the abilities of these large models to increase our performance. Okay, so last example is regarding the counterfactual data augmentation. So that is really ancient history that you may have recalled that Aahlad and Maggie talked about these medical notes. We talked about this problem of spurious correlation with writing styles of caregivers so the spurious correlation between these writing styles and the conditions that patients have. And we want to classify from these notes. And there was a suggested method by Aahlad that perhaps we can give each caregiver to rewrite the other one's notes, and then to obtain this augmented data set where the writing style doesn't play a role anymore, where we can do this counterfactual augmentation. Of course, getting different doctors are busy with more important things than rewriting each other's notes. So how to actually do that in practice is a big question. And here is an alternative way. The plan is maybe, So the alternative way is, what if we just ask an LLM to make this note for us? So it would go something like this. We would give our LLM a set of notes from a doctor and tell them they are this doctor. And this doctor maybe, as we said, writes man instead of gentleman, and treats people with high blood pressure. And then we will give it a note by the other doctor, Dr. Alice, and who writes gentleman and low blood pressure, and we'll ask our LLM to reproduce this yellow note in the style of the blue ones. So what we'll obtain is this counterfactual note that will switch both man, but it also switches the high with the low. So if you remember, like, low blood pressure is actually the medical content that we maybe want to preserve, but this type of model, it doesn't know what to distinguish between what is a medical fact and what is and what is actually writing style, so it might switch both. And this is maybe a toy example. The real thing that happens in these problems is that doctors use this type of templates, and when you try and actually do this type of data augmentation naively using an LLM, it confuses a lot of things about these templates between these two nodes. So what happened here is pretty much that the role of the blood pressure plays the role of a confounder. It is a common cause of getting sent to a certain doctor. So because I have high blood pressure, I might get sent to a certain doctor. But also it will affect what's written in my note, because my note might mention things about that blood pressure. So what the offers, if we just use this method, we can see here results on the out-of-distribution generalization task that Maggie just mentioned earlier. So these are many, many methods. On the left, it's just doing ERM. So these are the bars, the bar on the left. And each set of bars, the left is on mimic. So this is in-distribution general performance. And the set of bars on the right is performance on out-of-distribution. So it's a different data set, either I2B2 or a private data set from this work that's in collaboration with Google. So the data set is private. So we see that ERM suffers a huge drop, and we have different methods here. So the kind of prompting solution I've mentioned now is the most right bar, and we see that maybe there is a slight gain in out-of-distribution performance over ERM, but it's about the same as all of the other methods which we talked about today, like group DRO and IRM. But can we still maybe use our language models if we maybe just use them a bit with a bit more domain knowledge? And the insight here is just that maybe we could use techniques from causal inference. So the question we are asking is a causal question. We want to ask, what would a certain note look like had a different doctor written it? And the causal inference literature actually develops a lot of tools and methodology to maybe try and tackle that. So the suggestion here is maybe we could get inspiration from the tools of this community to kind of tailor them to our use with large language models and to improve performance in our problems. So there are two types of methods that are suggested in this paper. So the first is if we know that blood pressure is a confounder, so we might want to do what's called control this confounder. So instead of just including all of the blue notes of Dr. Alice in the training set of, or in the examples for the language model, we might just include those that have low blood pressure, which is the same blood pressure that our patient with the yellow note has. So we are matching our patients on several properties. So in the paper, they match that on many things, like the drugs that people take, or blood pressure, and many other properties. And then maybe we would get a correct note, which keeps the medical information, but actually transfers the style correctly. And they have another method that's inspired by a method called differences and differences that actually uses a timeline of the kind of temporal structure of notes in the hospital to do a type of vector algebra that tries to correct, and when we match two patients that were treated by the same doctor at one time and then a different doctor at the other time. So this is just a general, to get a general feeling of how these methods could work and kind of how can we, in a sense, engineer our way to get better approximations of these augmented data. And if we look at the results from these methods, so on the far right, we can see a pretty impressive increase in the out-of-distribution generalization. So ending on this positive note, ending on this last part of the tutorial, we pretty much saw that scale has certain promises and also certain pitfalls, and it's an interesting way forward to navigate these different things about scale. So, okay, so to recap what we saw in the tutorial, we started with an intuition of what are spurious correlations, how they come about, where they manifest in our current systems. And then we went on to a formalism to look with different graphs and aggregations and build out some language to talk about these. We moved on to methods that Aahlad kindly presented. And the methods were fit very nicely into these little cookie-cutter problems of different graphs that we have and simple scenarios that we might consider, intuitive ones. And then we kind of showed that perhaps things in real life are not that simple, and maybe the formalisms and the assumptions we make are not very practical. And this relates to benchmarks and graphs and all of the things we talked about. And then, of course, scaled and foundation models or large models came into the picture and also kind of reshaped the type of questions that we can ask and the type of solutions we can give. And the questions we will leave you with is, okay, how can we take these things and go back to the drawing board, come up with good formalisms, good methods, and insights about this problem. So we also leave a set of open questions that were raised during this tutorial, so you feel free to scan those later when you maybe check out the slides. And as a final note, we would like to thank Rajesh Ranganath and Mark Goldstein for their help with developing these tutorial materials. And thank you, everybody, for your attention.
All right. I'm going to invite our panelists to come up, and we'll take questions at the very end after the panelists, after the panel discussion. All right. Thank you all for being here. We really appreciate your presence. Also, this is super exciting because all three of them are really incredibly cool. So maybe we'll start with, can you give us a quick 2-sentence introduction about who you are? I'm going to start with Aditi.
Okay. Hi, everyone. My name is Aditi, and I am a professor at Carnegie Mellon. And I've been working on various aspects around robustness and reliability from the pre-foundation model days of like many years ago. And I'm excited to be here.
Thanks.
Hi, I'm Ilan Rosenfeld, and I am not quite as well-versed in this area as Aditi, but I have also been working in this space for quite a while now, and I'm very excited to be here.
Where are you currently?
Oh, right. Yes, I'm at Google right now. I just graduated from Carnegie Mellon.
Go ahead.
Hi. Sorry. Hi, I'm Danica. I'm a professor at UBC. I'm also a CMU alum. I guess it's only CMU people today.
We did not plan that.
But I've done a couple of papers relevant directly to this out-of-distribution generalization stuff, kind of IRM stuff, one of which was published and one of which we abandoned because we couldn't get it to work, which maybe I'll talk a little more about.
That sounds familiar.
And I've also done some closely related stuff in like conditional independence testing.
All right, maybe we'll start with sort of the last theme that was in the tutorial. What are ways in which you've seen the scale issue or the scale idea work? And what are settings in which you didn't see it work? And do you have thoughts on whether or not we should kind of like hope that scale answers all our out of distribution issues? Ilan, because you're smiling. You go first.
I'm just having a good time, but I'm happy to go first.
Yes, please.
Yeah. So I think it is, quite impressive how much scale seems to handle a lot of things. Yoav pointed out several failure modes that definitely exist, and I don't think that those are going to go away. I think it's like there's a lot of issues that are sort of here to stay, and they're sort of case by case. But the nice thing that scale provides is there's a lot of like tail behavior that we start to sort of see in our training data as we scale up, and then now we know how to handle that training data. And so scaling just enables us to handle that more effectively, but in scenarios where you really care about the ninth decimal place, like it's very important, I think that scale is not really adequate to address those situations. So in these like fuzzy scenarios, I think scale is great. But we do still need to be thinking about other approaches to solving the problem.
Great. Any other thoughts?
Okay, just to add to that a little bit, I think when we think about scale, we're sweeping a lot under the hood about what is the kind of data, what is the kind of objective that we're scaling these things on, and I think it doesn't come for free. Like the fact that we're able to scale things up is because we're okay with unsupervised data, lightly curated data, and so on. So at the end of the day, we still need to adapt these models to whatever task we want them to do, and that is not going to be something that we can scale up because that requires careful supervision, careful thought about what do we want from these models, and from a lot of the things that we've seen, even if we train models on lots of data, if you're trying to steer them or get them to do some downstream tasks on limited data, they are not, we still have all of those problems again. But maybe we have a better starting point because the model knows something, but it knows something in this vague sense of scaling up the data, but not in the way that is necessarily what we want.
To bounce off of Aditi, I work a lot with healthcare data sets, and I am not kidding when I say my collaborators will sometimes come to me and be like, hey, we want to know something about this very rare disease. And I'll be like, okay, what kind of data set do you have? They have we have the largest data set on this. How big is this data set? 200 patients. And they're very excited about it. I'm like, all right, let's see where we can go from here. But in these very rare settings, your model just has not seen anything like that before. Any other thoughts on scale?
Just one quick thought, I guess, is what we think of as out of distribution in distribution changes with scale, right? So things like draw me a unicorn in ticks, which is a problem a lot of people have thought about with LLMs. That's out of distribution for reasonable amounts of looking at the internet, but if you include the whole internet, that is a thing that is on there somewhere, right? And so the framing that we think about of what does out of distribution generalization actually mean, I think changes. I think it's not obvious that we really care about out of distribution problems. Well, depends on the problems. Things like medical stuff, absolutely. For things like getting the LLM to give you the answer you want, it's not clear what is out of distribution and what is just some rare part of the distribution that you haven't seen very many or any samples from.
Wait, so are you saying that as the scale of the data set increases, basically almost or a lot of things will become in distribution?
Yeah, I think so. I think the distribution of questions that people might answer on the internet is really big,
Yeah.
right? And you can ask a specific question that you can be confident nobody's ever answered on the internet, but is that out of distribution, or is that just, oh, I didn't happen to see a sample, but it's really the same distribution, right?
Yeah, that's very fair. I guess to all three of you, do people use or have you seen people use the out of distribution specific methods in real applications? So whether that's in industry, I don't know if you, Elon, can tell us anything without killing us, but like, are you able to share, for example, settings in which you've seen industry use this? And this is not just for Elon, it's for all of you. Are there practical settings where you've seen people use methods for out of distribution generalization, whether or not they worked?
I think so.
Choose your words carefully.
I have a very limited view, at one company as opposed to like in the entire space of industry, what people are doing. But at least in my experience, I think the only things that I've really seen are things like domain adaptation techniques, things like self-training. And I think that, there are a lot of methods that we think of as more sort of for out of sample generalization, like data augmentation, and those, also help with out of distribution, right? Like there's this strong correlation between those performances. So I think those are examples of things that you could argue are methods for improving out of distribution generalization. But as far as methods that sort of seem to be sacrificing performance in distribution for the purpose of robustness, I think, at least in my experience, it's really hard to sell some of those ideas without a very strong evidence that it's going to pay off in some other metric. As we've seen in some of these very sobering looks at recent empirical evaluations, there don't seem to exist methods that really seem worth it. So, I'm hopeful, but in my experience, I haven't seen much like that.
Okay. Other thoughts?
I mean, I feel like some of these questions are a bit hard to answer because they're not very well defined. It's like, what is out of distribution versus out of sample, test set, whatever. And I think at the end of the day, people care about certain evaluations. And like for what I've seen in the safety side, it repeatedly, there are like these jailbreaks and there are these examples. Like, for example, I think the original GPT models weren't very good at not being toxic in like minority languages, for example. And then they were fixed. And now you can say like, if they went and collected targeted data and fixed it, like, is this, I don't know, do you call this an OOD method? Like, I don't know. So I feel like, but that to me is an example where like it was a thing that you wanted to work well in the real world across many settings that go beyond what your training data was collected on, and they had to go and figure something out. In some cases, it could just look like just collecting more data, and like that's one way to fix the out of distribution problem is just like make it in distribution. Some cases you can do that, but I bet in some other, and all the methods that you develop, like, you could imagine that you could call them out of distribution methods too, so.
Yeah, so when you say like collect more data, I guess, is this data targeted for, like, I know that this specific so I think I would call that out of distribution, because unless you're going out and just like wholesale, I'm going to randomly sample, I would not probably call that out of distribution, but yes, I think you are getting at like there's more of these like data collection rather than like methods.
I think in industry there's, obviously there's this much greater emphasis rather than on novelty or, like simplicity. It's just what works.
Yeah.
And it's been established that if you go out and you identify like what is the problem we're trying to solve, let's gather examples of this thing that makes our model fail and add it to our training set, and that solves the problem.
Yeah, but even like the analysis of what makes my model fail. Like if you end up realizing, well, this model is failing because this specific subpopulation is very underrepresented in my training data, or this specific nuisance variable tends to be correlated with things that I care about. That kind of targeted data collection also, like, it requires at its core reasoning about what is the
Yeah,
so
absolutely.
I think I think that's valid. I think we will still have jobs. This is good because I think going out and wholesale kind of sampling at random is expensive and it's hard. So doing that, or like if what we get out of OOD generalization methods is a way to sample efficiently, that is I think in my opinion that's a really good contribution. So maybe that's another kind of like I wouldn't say entirely new, but open area of research on like how do you sample things or sample data, to be specific, in a way that improves or directly addresses your failure modes that are related to out-of-distribution changes.
And just to add one more thing, I think this is like probably the number one takeaway that I've learned through all of my work in generalization is that like there is no one-size-fits-all solution, and the methods that work are going to be the methods that are tailored to your specific use case. And I think it's kind of if we design these benchmarks where we just look at like average performance on all these different things, and we saw there's this evidence that like a lot of them are like not really correlated or even anti-correlated, it just doesn't seem the right way to go about assessing the efficacy of a method, to just evaluate it on a whole bunch of things. It's really a case-by-case basis.
Sorry. I wanted to add one thing that is different, I think, in practice is, okay, so speaking of benchmarks, the way we evaluate in the robustness literature is like we're allowed to give like one model typically, and then you look at how it does across many things. But I think in practice, the models are constantly updated, sort of like the targeted data, collection, like models are updated. So I think thinking about like what's the right overall protocols we need to do to like efficiently adapt these models, I think people are thinking about those things a lot, and I believe there are new terms for it, like mid-training, post-training, whatever. So I think all of them, that's like a practical challenge that they're dealing with. And I think that's something that maybe having a static set of benchmarks and asking for like one model to work doesn't entirely capture.
Yeah, this is kind of going back to exactly what we're saying. These benchmarks are very, very different, and your model, like one should not expect one model to perform well on this like wide swath of benchmarks that have very, very different assumptions baked into them. So that's very helpful. I guess like going back to something that you were saying, Elon, there is a sense of like the models need to be bespoke, or like they need to be targeting specific distribution shifts or specific scenarios, which gets at a lot of the out-of-distribution work kind of bakes in known assumptions. So assumptions about the graph, like we were talking, assumptions about auxiliary label, and I feel like there's a tension here. There's a tension in that like the general machine learning literature has for a very long time kind of argued for, no, we let everything be data-driven, we let the model decide, we let the data decide. But I think in general, and you can disagree with me, the out-of-distribution community has focused on, well, I know something about this problem. Like I know something about the distribution shift, I know something about the vulnerability of the model, and I'm going to bias the model using my knowledge, not the data, my knowledge, to make it work better. And I feel like that's viewed sometimes as a critique of the OOD generalization literature. Do you think that's a limitation? Do you think that's a good thing? Do you think that's something that we should strive to get rid of? Or do you even think that that's not a thing, we don't do that? There are many methods that don't require knowledge. Go ahead, Danica.
So just to comment on that a little bit, every machine learning model, everything we do is based on some kind of assumption, right? A lot of the present deep learning stuff, not specifically thinking about OOD, is very based on this IID assumption, right? And when that's not true, the way to get more data and scale to not make any assumptions about how environments are changing and just learn how they change would require, well, I don't know if it requires, but one way you could think of doing that is doing some kind of meta-learning where you have lots of environments and you learn how to adapt to new environments. And that's the thing people have studied. There are some settings where that makes sense, but there's a lot of settings where it doesn't make sense, right? Where maybe we have a ton of data, but we don't have a ton of IID sampled environments. Yeah. And so the trying to bake in knowledge about what's happening is a way to deal with environment scarcity rather than total number of data point scarcity.
Yeah,
right?
Absolutely.
And if you don't assume anything, you can really trivially, see that the problem is impossible, right? You have to assume something.
Yeah, totally.
I guess another aspect is whether we want worst case or like average case performance. So I think if you really have a constraint that you want to satisfy like in the worst case, then we need to find ways to bake in, and we can't just like sample data to show that, because then we don't get that kind of worst case guarantee. And I think the bigger question is like, do we want a worst case guarantee against like an assumption that's not perfect, or do we want to just like give it away? And I think that's a question that depends on different settings, and I can find cases where both are better.
Yeah, I think I totally agree with all what you're saying, and I think it's almost like getting dinged for making assumptions. It's just getting dinged for being explicit about your assumptions, like you were saying earlier. We make assumptions, but I think these are useful. Well, I'm obviously biased, but I think these are useful and they're necessary to make progress.
Yeah, I think if anything, like you said, I mean, there's always assumptions, even in the IID setting, and I think the reason that we're sort of more aware of this element in OOD settings is because we haven't figured out how to make it work yet. Whereas like in the IID setting, like apparently scale does seem to be just working, and so suddenly we've hit this moment where we're like, okay, well now we actually have to sit down and like make explicit what are the assumptions that we're making. So for sure, I don't think it's something that we can strive to get rid of. I am an advocate for sort of loosening them, like the point that Aditi made about like if you have an imperfect assumption and then you solve a min-max problem over that, now you're being extremely conservative in a way that could really hurt you. So I tend to try to think of ways to sort of relax them a little bit and how can we maybe make some data-driven assumptions in the sense that let's first dive into this data set and try to identify what patterns we can that maybe we can take advantage of. But I think it is sort of a little bit of a drawback that people sometimes try to think of these assumptions sort of in an abstract sense, like they form this graph without actually like working with the data at all. And it's nice to think like, oh, this is the causal flow of how the universe works, so I should expect it to hold. And that may be true, but if it doesn't actually get sort of compared with the data that you're working with, then it can definitely hurt you.
Yeah.
Can I just add on to that
sure.
slightly? So I think one of these assumptions that people often make, and this is a huge area of this kind of research, is this assumption that causal features will generalize better. And this is actually just to slightly criticize something for your tutorial. It's a great overview of stuff. There was this paper that you mentioned that's at this NeurIPS, Nostal, and Hart, where the paper, they took a bunch of different data sets and they did their best to identify which of these variables are causal and which ones are like, we're not totally sure, but we think they might be causal, and which ones are like, well, we think these are probably not causal. And then they said, okay, if you train only on the causal variables, does it do better? Does it do worse? And generally, just including everything did better. I think there was one exception where that was not true, but the case of the variable that you shouldn't include was very causal. And so it was a causal variable that was hurting you. And this is, I think, an assumption that a lot of people have internalized, and I think it makes total sense from like an ML background, but it's just not true that causal features are more stable. And so the specific bit of criticism is you changed their figure, actually.
Oh, no.
Is in their figure in their paper, I looked it up just to check, they said causal features, arguably causal features, and you changed that to say stable features, arguably stable features. Causal and stable are not the same thing.
No, I totally agree. I think we hand-waved it a little bit because we didn't want to dive into the exact definition of what is causal and what is not causal, but yes, the general connotation is like causal and stable. On average, are kind of correlated. Just to bring up something that I saw on Blue Sky a couple weeks ago from Yuri Shalit, something like I don't know, over there. Thank you. If you're diagnosing a disease based on symptoms, that's anti-causal, but it's very stable. Right? Whereas something what time you go into the hospital maybe affects which clinician you get, and then that affects what you get diagnosed with and stuff. And so that's causal, depending on exactly how you set up your variables, but it's extremely unstable. Yeah.
Right?
Yeah, sure. That's a very valid kind of fine point here is that causal models are helpful for a lot of things. The verdict is still out on whether or not they're helpful for out-of-distribution generalization or stability, to put it in a different way. Okay, any other thoughts on the topic? All right, so moving on to the next question. Are there trends or issues that you've seen come up in this literature that slow down the progress of out-of-distribution generalization? Are there things that you wish we can change? And if we do, you think we'll get to a better state of the research?
I think there is, but it was already covered a lot in the tutorial. Which,
okay.
Yeah. So this idea of, we're going to define a set of benchmarks and we're going to evaluate our method compared to other methods. And, of course, it's so easy to select the benchmarks where the, expected structure of the data generating process matches the implicit assumptions of the method that you're proposing, and so it works quite well. Or maybe you just tuned your hyperparameters a little bit better than you did for the compared methods. It's really hard to argue for anything else because the whole field as it is right now is completely driven by this benchmark style approach.
Yeah.
And it works so well in so many settings. And it's sort of this, this steady pace of progress. And I just think it, after 5-10 years of research and very little progress, seemingly on these benchmarks, we have to somehow peel ourselves away from this idea that there will be a method that just kind of beats every other method, and we have to maybe find a way to restructure the incentives to enable, papers that say we're going to pick this one problem and make really good progress on this one problem. And there are excellent papers that do that, but I think it's just it's the general reviewing atmosphere is not as accepting of that kind of approach, and I think we really should strive to make that more of the norm.
Yeah. Other thoughts?
I wasn't there for the benchmark part.
No,
of
you're
the
fine.
Tutorial. I kind of agree, and I think there's also another problem with OD kind of stuff is that it's supposed to be hidden, it's supposed to be unknown, and so we don't really have a way of capturing that. And I think one problem is that once you define a benchmark, you can trivially train on it. And so how do we draw the line between what is meaningful progress on the benchmark? And this is going even beyond just hyperparameter tuning, validity and so on, but just what approaches are truly targeting the unknown aspect versus what is targeting something that will work on this particular setting, but not on anything else that's useful. And I think that's really kind of a hard...
Yeah, I think, both of you raised points that kind of triggered thoughts. Aditi, when you say it should be unknown, the out of distribution distributions should be unknown. But I've had this conversation many times with different student collaborators. I'm like, okay, you cannot look at the test sets until the model is done. Until we have a model, the model is fixed, it's frozen, we're not changing anymore, then we apply it to the test sets that are out of distribution. Because it's just so hard, there is a human urge.
Exactly, yeah.
Of, okay, I printed out the results and I'm not going to explicitly use the data sets, the out of distribution data sets to improve my model, but I kind of saw that this thing leads to a little bit better performance on this out of distribution. And already, once you start doing that, you're already in a very unrealistic setting and you're it's hard for you to make a model that does not depend on the out of distribution. You make the out of distribution distributions in distribution, basically, by looking at that. The other point that was raised is the point of hyperparameters, and I hadn't even thought about that until you brought it up. A lot of the out-of-distribution approaches, you'll see when they're picking hyperparameters, they're either picking them on data sets that are for example, balanced. So if you're training...
Right.
Yeah, if you're training a model to look at water birds versus land birds, the validation set has balanced water bird. You're equally likely to observe a water bird on water or land background, and the same with land. That's one. Another thing that I've seen is that people don't even tune their hyperparameters. They're here is a family of models, and if you switch the value of the hyperparameter, this is the out-of-distribution properties that you'll get. Well, how do I use that?
Or even worse, they tune the hyperparameter and then don't say anything about how they chose it.
Oh, yeah, they explicitly do the process that I was saying earlier.
Yeah.
Yeah, so I think it's important to kind of make sure that the out-of-distributions are actually out of distribution when we're evaluating, and not sneak a peek into
sometimes the default hyperparameters you download from the GitHub repo kind of already leak something and you don't even realize. So, yeah.
That's another solution, I guess. Switching to a more positive view, I guess. If you had to point to one paper or idea that changed how you think about out of distribution generalization, what would that be?
Personally, for me, it was the IRM paper,
Okay.
which I guess I had seen some of the work about samples from some meta distribution, see what happens. But I think the emphasis that paper brought on hey, this doesn't handle some really interesting cases, was really reframed my opinion of those things. That paper had lots of issues. Both Ellen and I have written papers about problems with their scheme. But I think popularizing these ideas was really impactful, for sure.
I don't know if I can point to a single paper, but I think just idea-wise, I have over the years just become a little bit pessimistic about true sight unseen out of distribution generalization. And so I've kind of decided, like, let's do unsupervised domain adaptation. Let's sort of shift. We're imposing this extremely strong assumption of absolutely no knowledge whatsoever. Is that really even realistic? Like, why are we starting with this difficult problem if we don't absolutely need to? Maybe this is a little bit too pessimistic for a tutorial devoted to this topic, but I've started to feel that. Yeah, I think that I feel much more optimistic about how can we sort of relax this in, maybe we don't even see data from the distribution, but we know like some small fact about it that we can use. And I think that's sort of this thing that I'm trying to move forward with.
Okay. I don't know if there's a particular paper, but I think, I remember one thing that stuck with me was this idea that you can collect a lot of diverse data, and so there are things in the tails, but that doesn't mean the model learns from them. So I think it kind of dispelled this notion that you just have to go and collect everything and just a little bit, it's all good. And I think the fact that the learning dynamics actually plays a really important role into how does the model actually use this data, where in the training process has it seen these data points and things like that. And to me that was really interesting because it both said that there's no trivial solution, but it also says that maybe there is a lever in terms of understanding how these models learn, regularizing different objectives, understanding optimization, which I find exciting intellectually, but also it feels like it would give us ways to do better. So I think that general observation was interesting to me beyond just get more data and train the models.
Yeah, this is one of the areas that I'm super excited about these days. How do the training dynamics, and we talked a little bit about the geometry, but we didn't really go into the dynamics of your SGD. How does it change? Which I think is a really cool idea. How does it change when you impose these kind of different regularization schemes or out of domain generalization approaches? Yeah,
not to add anything insightful, I just want to say I very strongly agree. I think it's a very interesting direction. So for anyone who's interested in these topics, looking into the dynamics and how the model learns from the data and learns how to make decisions based on what it saw is a very promising direction, I think.
I'll just also add nothing and say I totally agree. I think this learning dynamics stuff is something that some of the students in my lab have been really looking into, and we haven't thought about it so much for OD, but a little bit. We have a workshop paper about it.
Yeah, great. Which workshop is it? One of
Positional
them.
generalization, I think. Yeah.
Check it out. Okay, I guess to add one quick thing, was something that I learned that I got really excited about is that, or not a specific idea, is that out of distribution generalization approaches can help with other tasks other than out of distribution generalization. The specific one that I got really excited about a while ago is finite sample efficiency. So if I train a model to generalize well out of distribution, it ends up kind of being very efficient in finite samples. So even if I don't care, I'm generalizing in distribution, there are some settings, not a lot, not all the settings. There are some settings where actually just doing something like a regularized model for out of distribution generalization would actually give you better in distribution performance. Okay, I guess one last question is the theory behind why some of these methods work has been around. I would say the earliest that I can remember is maybe some of Scheib and David's work in the early 2000s. Are there open questions or exciting areas that dive more into the theory that you think are still out there and would encourage people to dig into? I guess we just named one, but go ahead. No.
Yeah, I'll say absolutely. I don't know all of Shai's work on this area, but the stuff that I do know is mostly about how similar are the two domains, and then if you learn something on a mixture or one domain, and then how well does it generalize on a similar domain, which is really interesting. Mm-hmm. But I think it's more in the example you had in the tutorial of the like expanding to nearby distributions versus expanding to really far away distributions, I think of his work there, his and collaborators obviously, as kind of like saying, hey, we can kind of, the shape of this expansion is kind of bigger in directions that the hypothesis class aligns with, but it's still very much about this local thing. Yeah. And I think at least the work of his that I'm familiar with doesn't address this, oh, there's some feature that totally changes importance between distributions. I mean, the bound is still true, but it's not, like, doesn't really help, right?
Yeah. Okay.
And so I think the figuring out what are the kinds of graphs or however you want to frame it that correspond to real problems and figuring out what are the right theoretical assumptions that correspond to the kinds of things we actually see in the world, I think is still very much open.
Yeah, so to jump in on that, that's exactly what I was going to say as well. As I've mentioned before, this idea of like looking at the data and identifying what are the actual assumptions that are reasonable to be making. So I actually had a paper, I think at NeurIPS last year that did this, and in fact it was precisely taking a paper of Shai Ben David's but then updating it with like a slightly refined assumption that was based on some experimental observations, and then it allows you to give a bound that, is like practical and you can apply to real methods and it actually works. So I think that there is room. As I mentioned, I think it's kind of a common pitfall to try to start from a whiteboard and be like, what seems like a reasonable assumption, or what assumption would allow us to prove something, and work backwards. And it's very tempting to do that, and I know I've made that mistake many times myself. But I do think that there is room. It just involves working with the data as well.
Can I?
Yeah, yes, please.
Yeah, I have two things. So one is to throw a buzzword out there that's not to do anything with Shai Ben David, which is synthetic data, and I think foundation models and like the fact that we have really good generative models. I think this puts us in kind of a nice regime that we may not have to confine ourselves to a fixed training data, but we don't have a good way to think about the theory or, there are connections to things like self-training and so on, but I think putting things like synthetic data and data augmentation with foundation models on like a theoretical footing, I think it would be really practically relevant as well. The other thing that I wanted to say was sort of related to what came up earlier is, so I think none of the theory that we had earlier like really looks at the learning dynamics or like how our modern methods work. But there are also a lot of practical experiment or like practical findings that says that there is a lot of structure to how neural networks learn, but we don't really understand that. And I feel like it would be really interesting theoretically for us to actually take all these practical observations and make sense of them. An example that comes to mind is accuracy on the line and agreement on the line, and I do not today have like a picture for like why this happens, but I think it actually says something really deep about how these neural networks work, and it totally does not match these kind of divergence bounds that people would expect. Yeah. So I feel like kind of reverse engineering in terms of like what does this tell us about like what theoretically is going on could also be another interesting avenue.
Great. Okay, so we're going to open it up maybe to a couple of questions for our panelists and for Yoav and Aahlad. I can't see anything.
Yeah, these lights are...
The lights are incredible. I have been trying to use my hair as a curtain for a while in this tutorial, but yes. Maybe, I don't know if you... Okay, there's a question. There you go. Thank you.
Hey, thank you for the great panel. This has been a wonderful conversation to listen in on. How do you think about, like crisply, how do you define the difference between robustness and out-of-domain generalization? And then also, I'll drop this on your plate, how do you think about this in relation to adversarial generalization?
I would say I think of robustness as managing tails, and then I think of out-of-domain or out-of-distribution generalization as sort of these structured shifts that are substantially different in that, it's like fully a change in one hospital to another, as opposed to a patient who presents with a very rare disease that is not usually seen in the training set. And obviously they're strongly related to one another, but sort of the approaches that you take to improve robustness or improve out-of-domain generalization might be different depending on the different settings. And then I don't remember what the
Adversarial.
Oh, yes.
Was the last.
like. How does that relate to adversarial robustness?
I guess, yeah.
Is that right?
Yeah, I just dropped it on your plate because I just want to stimulate your brain because this is such a
Yeah.
great panel. I know that there's going to be a good answer somewhere.
Yeah, I spent a while working on adversarial robustness. I think that honestly feels like a fundamentally different problem.
I agree.
It's sort of more an artifact of the structure of neural networks, and I think it not that it's not in its own right an extremely interesting and difficult problem to pursue, and I think that making progress on it would entail or perhaps would require a deeper understanding of how neural networks learn and why they learn, what they learn, et cetera. But it does feel like fundamentally not the same sort of question. And so, yeah, I think I would probably approach them as sort of two separate fields.
I might disagree with that a little bit, in that I agree the day-to-day practice of working on one versus the other is fairly different. But I think fundamentally they're both about working on different distributions than you're training on, right? And in the adversarial one, the ball that you want to be robust to has a very different shape.
Sure.
Right? It's like being robust to L infinity.
They can both be framed as optimization problems over an uncertainty set of distributions.
Yes.
Yes.
Yeah, I guess maybe one nuance is, I guess I'm picking the in-between position here, which is that for OOD, I think of it as the world is kind of chosen first, and then you get to choose your algorithm and response.
Yeah.
But if you're adversarial, then I think we have to be in a setting where the adversary can respond to your algorithm, so it kind of puts more pressure on you. It changes the question in that way. But I think a lot of whether it's low-level abstraction of pixels versus higher-level semantic changes and stuff, I think those definitions are a bit of artifact of how they came up in the research community, and they're less definitional. But I think the difference I see between those two is kind of what I said earlier. Yeah.
Okay, cool. Just one follow-up, which is a comment. I think there might be some relationship between the two. There has been some work showing that it was sort of a survey evaluation of existing methods to make networks robust adversarial examples, and they showed that, I don't know the citation, but they showed that early stopping gave you the sort of the best Pareto trade-off between in-domain and out-of-domain. So there's something
There's
going on.
absolutely a connection.
Yeah, I didn't
there's
mean to
something going
suggest
on
that they were unrelated.
Yeah, no. Your answer was still quite good. Thank you very much.
I think, just to add to that, I think adversarial robustness, OOD, fairness, privacy are all kind of the same problem. And we're looking at it from different aspects for each of those things, but they're all very closely related. Yeah.
All right. I think I see. I'm not sure. Yes, go ahead, please.
Yeah, just a quick question, which is probably a bit hypothetical because, so if we have AGI at some point, how this discussion can be related to that? Would it make all of these discussions obsolete, or how would they change in that regime?
What is AGI?
Yeah, it's not defined.
Exactly.
Yeah, artificial general
I
intelligence.
mean, we could define AGI as models that aren't susceptible to distribution shift, and then
Yeah, exactly. Because I was thinking it in the frame that it's a oracle model that knows everything about everything. Is it correct?
great. Let's all go home.
I think by the time we get to that model, let me put it this way, there is going to be a bunch of other bigger problems than maybe out of distribution.
Okay, got it.
But yes, I think it's a little bit hard to define what AGI.
I would say that just to maybe try and take a real stab at this, I think once you have a model that isn't making these sort of silly mistakes that we can easily look at and be like, it's clearly using a shortcut. The next question is, how do we make sure that a model that is making the correct decisions is making them for the same reason that we think it's correct, right? So basically the question of alignment to our values. Because, when a child is told by their parent what to do multiple times and the parent is looking out for the best interests of the child can trust the parent because, there's a reason to believe that their incentives are aligned. When we have AGI that's making these decisions for us, how are we going to be able to trust that those decisions are for the right reasons? And so I think those are kind of that's sort of how I would relate out of distribution generalization to a future where AGI is achieved.
Yeah,
in my
kind of
best
to
effort.
go off from that, like I could claim that like the models we have right now are AGI in that they're doing what you ask them to do really well. Like you ask them to solve, minimize loss on your training set, and they're doing great at it. And so it's like kind of really hard to draw the line between are they going wrong because we're optimizing them for the wrong thing, or are they kind of not doing it right? And I think, like that's the exact question that's going to now come up if we want to frame it in terms of they're really smart but doing the wrong thing.
Right.
All right, well, let's thank our panelists, and I think this wraps up our tutorial.